Hello and welcome. I am Karen Fox with NASA's Office of Communications, and we are here today at the Smithsonian's National Air and Space Museum in Washington, D.C. for a live media briefing about NASA's TEMPO mission. Now, TEMPO is a partnership between NASA and the Smithsonian, and that stands for Tropospheric Emissions Monitoring of Pollution. So TEMPO is a next-generation, high-resolution instrument to monitor air pollution. It is catching a ride on an Intelsat 40E satellite, which will put it into geostationary orbit over North America. It is set for launch in April of this year on a SpaceX Falcon 9 from Cape Canaveral in Florida. We are going to have remarks from a variety of experts, and then we will take questions both from in the room and on the phone line. Our speakers today are Chris Browne, who is the director of Smithsonian's Air and Space Museum, Ellen Stofan, the Undersecretary for Science and Research here at the Smithsonian, Karen St. Germain, the Division Director for Earth Sciences at NASA headquarters in Washington, D.C., Caroline Nowlin, atmospheric physicist at the Center for Astrophysics, Harvard and Smithsonian, Barry Lefer, who is the program scientist for TEMPO at NASA headquarters, Laura Judd, Applied Sciences Health and Air Quality Associate Program Manager at NASA Langley in Hampton, Virginia, and Erica Wright, who is an education specialist at the Center for Astrophysics, Harvard and Smithsonian. I'll invite them up to speak, and afterwards we will start the questions. Thank you so much.
Thank you, Karen, and good morning. I'm Chris Browne, the John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum, and welcome to this national treasure. We like to refer to it as America's favorite museum. We're here this morning to talk about an exciting new space mission that our very own Smithsonian Astrophysical Observatory is leading in collaboration with NASA. As you'll hear from this morning's speakers from the Smithsonian, SAO, and NASA, the TEMPO instrument will monitor major air pollutants across North America every hour of the day, helping us better understand our planet and the impact we're having on it. Here in the museum, we tell stories of people and spacecraft venturing beyond our planetary home to discover what beckons us from afar. Later this month, the museum will be honoring the Apollo 8 lunar module pilot, Bill Anders, with its Michael Collins Lifetime Achievement Award. Bill is known for many accomplishments, not the least being his picture of the Earthrise over the lunar surface that some have argued set the modern environmental movement into motion. He is noted for saying, "We came all this way to explore the moon, and the most important thing that we discovered was our Earth." Bill knows firsthand the way our ventures into space inform us about our home planet. Examples of this are highlighted in our new gallery, One World Connected, which explores how satellites and other spacecraft have provided a new perspective of Earth as humanity's home. From satellite imagery that revealed the hole in the ozone layer to the satellites whose near constant imagery reveals the changes in our environment. Just as Bill observed, One World Connected illustrates how it is often easier to see the impacts of our actions when we travel far away and look back in. After this morning's briefing, I hope you'll take some time to explore that gallery and all of our other new exhibitions. That we have stories to tell in galleries like One World Connected is due to the important work of engineers, scientists, and explorers constantly developing innovative technologies and conducting groundbreaking research, pushing the boundaries of what is possible and expanding our knowledge of Earth's ecosystems, which brings us back to the TEMPO mission and why it is so important. To help us further understand its promise and significance, I'd like to now introduce Dr. Ellen Stofan, the Smithsonian's Undersecretary for Science and Research. Ellen?
Thank you, Chris. Good morning, everyone. It's appropriate that we're here in a museum today because the people behind Tempo are making history. It may not seem as flashy as some of the stories told in these galleries, but the methods and motivation and innovation that have gone into this mission rival any moonshot. Our country's brightest scientists and engineers are working with top-flight industry partners and government agencies to solve the small steps that go into overcoming seemingly insurmountable challenges. Poor air quality impacts us all. Each year, air pollution causes more than 60,000 premature deaths in the United States. Healthcare costs for illnesses caused by poor air quality top $150 billion, which is only a fraction of the toll it takes on our larger economy. Air pollution corrodes infrastructure, damages crops, lowers worker productivity, and limits growth. Essentially, it's an enormous danger for people and prosperity alike. Globally, it's even worse. More than 4.2 million premature deaths linked to air quality are reported annually. And just like in the United States, these devastating impacts fall disproportionately on marginalized communities. And it's not just confined to smog in large cities. People who live and work closest to the land, farthest from the urban centers, like farmers, ranchers, hunters, and fishers, will feel the first and the most significant impacts to their way of life from increased environmental disruption. The Smithsonian is working to combat that disruption through an initiative called Life on a Sustainable Planet. This program harnesses the vast global network of Smithsonian Science Centers, collections, and researchers to address losses in biodiversity, dangers to land and seascapes, and threats to the complex interconnected biomes we all rely on. Another focus of Life on a Sustainable Planet, perhaps the most important one, is engaging the public on issues of environmental justice. Tempo's data will measure air quality coast to coast, but this mission will do more than that. Pollution distribution mirrors a multitude of issues and inequalities facing millions of American families. By advocating basic human rights like clean air, we hope to empower people, especially young leaders and activists, to bring positive change where it's needed most. We want to create breathing room for young people to find solutions that speak to the experiences and priorities of their own communities. The kids can turn this thing around, and we owe it to them to provide every tool at our disposal. One of the underlying themes of Life on a Sustainable Planet is optimism, and I know you haven't heard much of that from me so far, but positive change is in the air. 60,000 Americans dying from preventable diseases caused by air pollution is appalling and unacceptable. But in 1990, that number topped 100,000. In one generation, we have cut this tragic statistic almost in half, and we're not stopping there. That's why I'm particularly proud to stand here today as the Undersecretary for Science and Research, because progress is happening and true sustainability is possible in our lifetimes. There are more than 1,000 Smithsonian scientists working on environmental issues around the globe, and the Smithsonian Astrophysical Observatory team heading Tempo is leading the way. In terms of value, Tempo outshines many of the historic missions on display around us. Low cost, high yield, and immediate use. Tempo will return critical data from day one, and hundreds of communities across the nation have already signed up to use it. Unlike the delayed gratification of a mission to Pluto, we'll get the good stuff right away. All this innovation and empowerment is possible because of our partners. Tempo will measure air quality across the entire continent, and the team behind it is just as broad. The spacecraft was built by Maxar in Palo Alto, California, and the instrument itself comes from Ball Aerospace in Boulder, Colorado. The launch atop a Falcon 9 rocket from Kennedy Space Center. Intelsat will operate the instrument just over the river in McLean, Virginia, and transmit the data to the Smithsonian team in Cambridge, Massachusetts. They'll process it and provide it to end users in communities across the country. Then it will be cataloged and archived at NASA's Langley Research Center in Hampton, Virginia, where the program is managed. All of that happens once an hour, every single day. You'll be forgiven for thinking all this critical work was happening from a new and expensive proprietary satellite, but it's not. TEMPO is a hosted payload hitching a ride to geosynchronous orbit aboard Intelsat's IS-40E communications satellite, which will provide more robust and reliable Wi-Fi connectivity to commercial air passengers and vehicles on the move in remote areas. It's only mid-March, but as Undersecretary, I've already spent about 80 hours on airplanes this year, so I love everything about that. I also love what TEMPO signifies. The fact that this critical instrument is integrated into a larger commercial enterprise, the way that the data will be parceled and shared, the sheer number of people, agencies, and companies involved. This is how we're going to save the world, by making this mission a part of our everyday work, part of our business, and part of our daily lives, by organizing and measuring our progress hour by hour and holding ourselves accountable for positive change. That's how we'll lead the world together in a 21st century moonshot and achieve life on a sustainable planet. Now it's my pleasure to introduce the Director of NASA's Earth Science Division, Dr. Karen St. Germain. Karen.
Thank you so much, Ellen. It's so great to be here. And let's see, cue the slides. Maybe? There we go, from NASA. All right, so I am thrilled to be here for the TEMPO launch event. TEMPO will join the family of 25 missions we have on orbit today. They're depicted in green and blue, and it's one of the 4 that we're going to launch over the next year. Those that we are building are depicted behind me in orange or gold. And, I think of NASA Earth Science in many ways as NASA's best kept secret. This fleet of satellites, or each one of them, is a specialist of some sort, and they're all observing different attributes, different aspects of the Earth system so that we can understand how the whole system works together. As the first ever Earth Venture instrument out of the Earth Venture program, the TEMPO mission is a prime example of NASA's Earth Action strategy, or Earth Science strategy in action. It starts with, at the bottom of the pyramid, developing innovative technologies that enable new and better and more complete observations of our home planet. Those observations underpin the fundamental understanding of how the Earth system works. And when you understand, you can build predictive models that can then be put into the hands of those decision makers at all levels of government and in the private sector and in communities to make science-informed decisions. We call this the high-value science chain. And so from the bottom of the pyramid, new technologies and observations through understanding, models, applications to solutions, and getting the information out. NASA has 50-plus years in Earth science and climate data archives. And as more federal agencies incorporate climate resilience, adaptation, and response into their operations, NASA Earth Science is powering those programs. In agencies like NOAA, the Environmental Protection Agency, U.S. Department of Agriculture, FEMA, Interior, and more. In the case of TEMPO, we're really proud to say that NOAA and the Environmental Protection Agency will be early adopters of the TEMPO data to enable their missions moving forward. And of course, underpinning all of this is our open and accessible data, and not just the data, but the science and the information that creates transparency and trust in that information. So we're developing at the top of this pyramid the Earth Information Center, the first phase one of which will open in June, and that's intended to make our information, our science, even more accessible to people across the country and around the globe. So Tempo's data will be fed directly into the Earth Information Center and enable those activities. And finally, Tempo is helping NASA move to the next generation of Earth observation capability and understanding our climate. Again, we study the Earth as a system, the land, the ocean, the ice, the atmosphere, and how changes in one part of the system affect the rest of the system. So as Tempo joins the other 25 missions, it will also form the foundation for the generation we're just starting to build now. And so that we intend to launch by the end of this decade, just making sure it's up there, the Earth System Observatory. And so again, the Earth System Observatory will stand on the shoulders of the missions that we're launching today and those that have been operating for us. The Earth System Observatory will again be that next generation to ensure that we are as well positioned in 2030 as we are in 2022. And I want to end by echoing Ellen's comment about optimism. We have in our hands the information we need to make scientifically informed decisions that tackle the problems that are in the challenges that we're facing today. I too am optimistic. The entire NASA Earth Science team is there trying to drive forward well-informed decision making as well as the fundamental science on which we build. So with that, it is my pleasure to hand the stage over to Caroline Nowlan to talk a bit more about Tempo Science. Thanks.
Well, good morning. It's great to be here. My name is Caroline Nowlan. I'm a scientist at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, which together with Harvard University forms the Center for Astrophysics. But this morning my job is to talk about Tempo in more detail. I have a slide too to go to. So first a bit of background. So we've actually been making these kind of air pollution measurements for over 2 decades from what we call low Earth orbiters. So the satellites that we're currently using are orbiting the Earth at about 700 kilometers above the surface and about 14 to 15 times a day. And these orbiters go over a particular place on Earth, usually at the same time of day. So every day we can get measurements, say, over New York City at 1:30 in the afternoon. But that's just one data point over New York over a day. And a lot is happening in New York City over a day. So we have 2 rush hours that we're not able to capture. And so the great thing about Tempo is that for the first time we'll be able to make hourly measurements over North America. So we'll be able to see what's happening over a whole day as long as the sun is up. And the reason we can do this is because we're launching Tempo on Intelsat 40E into a geostationary orbit. And a geostationary orbit is an orbit where the satellite goes around the planet at the same time that the planet rotates. And so we can essentially hover over the same location on Earth. So we can look at North America over the whole day. And the other great thing about Tempo is that we're getting down to really high spatial resolution. So as well as this time resolution, we're able to, for the first time, really see down to like suburban scales or neighborhood scales. At hourly resolution. And so in blue and orange behind me, you'll see these big boxes, and that's the spatial resolution that a couple of existing low Earth orbiter missions have right now. So you can see the pollution over the entire Washington, D.C. area in this case. But what does it look like on a fine scale? There is one existing mission, a European mission, that can see almost as good spatial resolution as Tempo, not quite, but it's, again, only once a day. So we're really getting down to these neighborhood scales now. So Tempo is a mission that's involved a lot of people. And behind me you'll see a couple images. On the lower right-hand side is an image from a recent meeting at NASA Langley, just showing a few of the scientists and engineers involved and administrators. But several hundred people have worked to make Tempo a reality, from universities, government agencies, state and local air quality agencies. and industry, of course, and from Canada, Mexico, the United States, and even further afield. In the top left-hand corner, you'll see a few colleagues from the Center for Astrophysics. And today with us are Xiang Liu, who's the principal investigator for TEMPO, and Raid Suleiman and John Davis, and they're happy to answer any questions you might have after the briefing as well. But TEMPO really was the idea initially of Kelly Chance, who's the principal investigator. Unfortunately, he couldn't be here today. But Kelly in the 1980s was one of the original developers of some of these low Earth orbit missions with a couple of European colleagues. And they were so successful that people started to think a few years ago, wouldn't it be great to put this into geostationary orbit? So geostationary orbit is a common orbit for weather satellites and communication satellites, but an air quality instrument measuring gases hadn't been there yet. So over a decade ago, NASA put out a call for science missions, and Kelly and some collaborators proposed TEMPO, and after a lot of work, it's ready for launch. Now, how do we actually make these measurements? And this is what I do at the Smithsonian Astrophysical Observatory. So on the left-hand side, you'll see an image of part of the inside of the TEMPO spectrometer. And the thing to note here is this beautiful rainbow. And so what we're doing is we're measuring reflected sunlight off the surface of the Earth, clouds, and the atmosphere. And the spectrometer breaks that sunlight into different colors. And then we use a detector to measure the strength of these different colors. And we can see what's in the atmosphere by the colors or the wavelengths of light that are absorbed. And we know from measurements on the ground in laboratories what the characteristic absorption features of different gases look like. And so we can't measure everything from TEMPO, so we're only measuring in the ultraviolet and visible regions of the spectrum. But luckily, there are a few air pollutants that have strong absorption in these regions. And there's several things that we measure. We don't have time to get into all of them today, but we have three main products that we measure, our gases that we measure, and those are Barry Lefer next will talk in more detail about these. There are various sources, but the first one is nitrogen dioxide. The second one is formaldehyde. So formaldehyde is not something that people think a lot about being in their outdoor air, but formaldehyde is really useful because it actually is a byproduct of it's a volatile organic compound. And when other volatile organic compounds break down in the air, eventually at some point they turn into formaldehyde, or formaldehyde is produced, and we can measure that from space. So we can use that information to infer emissions of other volatile organics. And volatile organic compound is a bit of a mouthful, but you are familiar with these. They're what make things smell often. So things like paint or gasoline or permanent markers, or even when you walk in a warm forest in the summer, it's volatile organics that you can smell. And the third thing that we measure is ozone. So ozone up high is great. It protects us from UV radiation and allows life to exist on Earth. But when ozone is at the surface, it's a pollutant, and it's harmful to humans and also to crops and ecosystems. And so next up, we have Barry Lefer from NASA headquarters, who will be talking more about the TEMPO measurements in greater detail. Thanks.
Thank you, Caroline. So it's a pleasure to be here today. And one of the things I wanted to stress is what you're seeing here is how TEMPO is going to be in geostationary orbit and scan from the east coast to the west coast during the daytime. And when it's doing that, what you're seeing here is nitrogen dioxide. And it's a byproduct of combustion. So when we're burning gasoline or coal or diesel fuel to move ourselves around, or electric generation plants burning coal or natural gas, a byproduct of that activity is nitrogen dioxide, and it's harmful to human health, and it's also critical in forming. It's a primary pollutant. It's emitted from the smokestack, and in the atmosphere it reacts to make ozone and formaldehyde, those secondary pollutants, but which are also harmful to human health. And so TEMPO is going to give us this ability to track chemical weather as it is emitted from sources and then transported downwind to other receptor sites. And so it's a really exciting opportunity to work with our other agency partners. The EPA and NOAA are part of the TEMPO science team, and we've been working closely with them to get the most out of the TEMPO data. TEMPO is not going to be in geostationary orbit by itself. What you see is a geo ring. TEMPO is looking at North America. Sentinel-4 is going to be looking at Europe, and the GEM satellite, which is also built at Ball Aerospace, is a sister satellite to TEMPO, and it has been in orbit for 2 years. And so NASA and the European Space Agency have been working closely with the Koreans who launched GEMS into orbit, working on that data, calibrating the instrument, validating the sensor. And so because the GEMS instrument has been so successful, we have really high hopes for TEMPO. And the TEMPO science team is going to be doing some measurements this summer and fall after launch, doing air quality studies over LA, Chicago, and New York to help interpret the early TEMPO data set and continue to monitor air quality at the neighborhood scale for many years to come. And it's my pleasure to introduce Laura Judd. Laura is part of our Applied Sciences program at NASA, and I'll let her finish introducing herself. Thank you.
All right. Thanks, Barry. Good morning, everyone. I'm Laura Judd. I'm a research scientist at NASA Langley Research Center, and I also serve as an associate program manager in NASA Applied Sciences Program Health and Air Quality Focus Area. So dovetailing from the overview from Caroline and the broader global view from Barry, I'm going to touch upon the work we've done to prepare for TEMPO with airborne observations, as well as the broader picture on how TEMPO data can help in public health and air quality management. So what I'm showing here are two images of nitrogen dioxide data. As Barry just stated, that is an indicator for fossil fuel combustion. And this is data that's been collected from the highest resolution satellite that is currently in orbit, which is ESA's Sentinel-5P Tropomi instrument. This instrument has a very similar spatial resolution to what we're going to expect from TEMPO, but as Caroline noted, it is in low Earth orbit, so we largely only get a picture once per day. And so that's what you're seeing on the left, which is a single orbit of data over New York City. This example demonstrates one of the challenges with satellite pollution data in getting gaps where clouds occur. Therefore, a lot of data analysis is done using multiple orbits, often averaged over months to years, which is depicted on the right as an annual average over New York City. So this averaging is often appropriate for a lot of uses of this satellite data, but it does smear out day-to-day variability, and it's, again, limited to the once-a-day early afternoon perspective. So the last decade, NASA's been collecting data with airborne simulators for TEMPO over major cities, with the strategy of measuring multiple times a day to see the evolution of pollution over that time frame. So this map here that has popped up on the bottom is a single day of data collected over New York City, and it also matches the same day of Tropomi data that is on the top. So this demonstrates the ability to get multiple chances to capture cloud-free skies throughout the day, as well as you can see how pollution evolves. This is a day where the pollution built up over the city, and as a sea breeze formed, it pushed a lot of that pollution inland, and what we're seeing in the afternoon is the continued emissions from major sources. And we've learned some lessons with these airborne data sets. We've unveiled how pollutants like nitrogen dioxide, formaldehyde, and ozone evolve from a top-down perspective throughout the day at unseen resolutions. And we've also gained confidence in our ability to validate data products at that TEMPO scale that we're going to get, which is essential for the adoption of data into stakeholder use as well as in research. We've been able to evaluate state-of-the-art chemical transport models used in air quality planning and identify disparities in air pollution emissions, just adding a tool to the toolbox working toward environmental justice research. So looking ahead to align with TEMPO's first summer of measurements, we are planning what's named the Synergistic TEMPO Air Quality Science Study, or STACS. And the measurement strategy is kind of depicted in the name as well as in the logo here, where we'll be stacking up our measurements from multiple perspectives from the ground, aircraft, and satellite in partnership with federal agencies, state agencies, and academic researchers. These measurements will help us accelerate integrating TEMPO data for better understanding the state of air quality in the areas we're going to visit, as well as the societal benefit of TEMPO data in the air quality observing system as a whole. So NASA Applied Sciences Health and Air Quality Program works to integrate Earth observations like those from TEMPO into the workflow of air quality management and public health organizations. So to engage with stakeholders, particularly for TEMPO, NASA established the TEMPO Early Adopters Program in 2019, and since then has enhanced interactions between the TEMPO science team and over 300 community stakeholders and end users that are interested in using TEMPO data. This graphic just depicts a few application areas and is certainly far from an exhaustive list that has been identified by these early adopters. In public health, TEMPO will expand studying the link between health outcomes and air pollution exposure to multiple times throughout the day. As I showed in my first example with our airborne data, pollution evolves quite a lot throughout the course of a day and from day to day. TEMPO data can be integrated into state-of-the-art air quality forecasting systems to improve upon alerting the public when air quality is poor. And we can also start to get granular enough information to identify gaps in our knowledge on nitrogen oxide emissions that contribute to air pollution, gain confidence in our models, and provide a unique perspective to our ground-based monitoring network that are used to make air quality decisions. And probably the easiest use for TEMPO data will just be the visualization of chemical weather, which has really only been seen so far from the glimpse of the aircraft images that we've collected, but will soon be available over broader North America. So that's all I had to share today, but I will now pass it off to our final speaker, Erica Wright, who's an educational specialist at the Center for Astrophysics.
Thank you, Laura. Good morning, everyone. I'm Erica Wright, and I'm an education specialist at the Smithsonian Astrophysical Observatory, which is part of the Center for Astrophysics. As we've mentioned, across the US and the globe, communities are still drastically impacted by air pollution. According to the American Lung Association, 137 million Americans live in areas with poor air quality. That's about 40% of the population. But that impact isn't spread equally. Certain groups, including historically marginalized communities and low-income populations, are disproportionately affected. The airborne TEMPO simulator data was able to show that information collected at a TEMPO spatial scale is able to accurately measure these disparities. In the data analyzed from the airborne TEMPO simulator instrument flown over New York in 2018, you can see this disproportionate impact with respect to household income. Here on the left, red indicates higher levels of nitrogen dioxide, and on the right, census data shows median household income, where dark green indicates lower income. You can see when you overlay these maps, the lower level of income corresponds to the highest levels of nitrogen dioxide. In this study, led by Isabella Dressel, an undergraduate student at the University of Virginia, scientists found that pollutant levels from nitrogen dioxide, which are emitted by vehicles and power plants, are typically 38% higher in low-income, non-white neighborhoods compared to neighborhoods with mostly high-income white residents. Similar outcomes that have been found in numerous cities within TEMPO's field of regard. And this is just one study from a field campaign and the Tropospheric satellite that Laura mentioned, both of which are limited in time. TEMPO, with its hourly scans, will allow us to study impact not just in the middle of the day, but as pollution varies in intensity throughout the day, as transient things like rush hour pollution affect various populations. We hope that once TEMPO data is regularly available to researchers, we'll be better able to evaluate impacts like these in cities and communities across the US so that they'll have the data they need to breathe easier. At the same time, the TEMPO team is working hard to measure what's in the air we breathe. Young people have shown the world that they're ready to lead the charge in creating a healthier planet. Youth leaders are at the forefront of much of the current environmental justice movement, seeking a more sustainable planet for us all. Through educational efforts at the Smithsonian, we aim to empower even more of their peers to seek environmental justice through the investigation of air quality by analyzing real-world scientific data sets like those from the TEMPO mission. While it's important for this data to be in the hands of researchers, it's also critically important for this data to be in the hands of our young people, so they and their communities can work together to make informed decisions. On screen, you can see some of the young people that the Smithsonian and NASA have engaged in our efforts to better understand our air. To support more teens in asking their own questions, I'm working with educators from across the country to develop resources that empower teens to pursue personally relevant investigations into their local and regional air quality. We're creating curricula and guides that help strengthen their skills with real-world data analysis and their understanding of air quality, so that when tempo data is made available on NASA interfaces like Worldview and an app being developed at the Smithsonian Astrophysical Observatory, they'll be ready to use tempo data to create healthier communities. As an educator, what I love about tempo is that it gives us a picture of our backyards, but also it shows us how we're all connected through the air we breathe. Together, we can build a better understanding of how communities are impacting one another and work towards healthier air for us all. Thank you, and I think we'll now move to questions.
Thank you so much to our speakers. I'm inviting folks up here to answer questions. We also have people in the room from a variety of our partners who are available to answer questions. A reminder to those of you on the phone, if you press *1, you can get in the queue to ask a question. But we will start with people in the room, and I think we have a mic for people if they wish to ask a question. So I will look out to the room. Questions from people here? Anybody have a go back?
There's a question.
There's a question? All right. Let me ask you to use the microphone just so everybody can hear you. Thank you.
What's the lifetime of the mission or the instruments, the sensing instruments aboard the satellite?
Yeah. So the NASA, we have a interesting way of describing the prime mission, which is what the tempo team is funded initially, and so the initial mission is only 20 months, but we know that GEMS has been operating for over 2 years, and we expect tempo to last many years. We don't know. It's one of our initial low-cost missions. It was on a firm. We had a firm fixed-price contract, and it was a cost-cap mission. But it's, so I don't know the answer, but we're expecting. I guess the short answer is Intelsat is planning to be there for 10 to 15 years, and we hope we'll be operating that whole time. Yeah, come up, Mike.
Come on up and introduce yourself, please.
So, Mike Fox with Maxar. The answer to the question on how long the satellite would last is 15 years. That's all right. Yeah.
I want you to stay up.
Yeah, sure. Okay. Was there anything else? Or?
I think we're good, but if there are other questions in the room, but please stay up here with us so you can ask questions.
I have a go back.
Then please, Barry, come on up.
One of the things I meant to say is that this integrated observing system that Laura was mentioning is really a key part of our strategy. Tempo is going to measure the total amount of pollution in the atmosphere because those photons come from the sun, reflect off the Earth, and go back to the satellite. And so we can just see the total amount of pollution, and the sensors that the EPA have are measuring at the surface. But the EPA is only measuring where their sensors are, and so Tempo is going to get this map of the whole country, but we still have to work with the EPA ground monitoring network, the air quality models that the EPA and NOAA and NASA all have. So it's this combination of satellite plus ground observations plus these models that really give us this understanding of what the air quality situation is in the United States, and then help us to forecast what it's going to be for the next few days or for the next few decades using our different modeling systems. I'm going to let Caroline answer that. It's got 2 detectors.
And would you repeat the question?
Oh yeah. So what is the wavelength range? And Raid can help me here, but it's is it 340 to or 280 to 500, and then 540 to 780 something? Go ahead.
Yeah, it's from 290 to 494 nanometer. Then another channel from 540 to 740 nanometer.
Yeah. So 290 to 492.
Yeah.
Okay, and then 540 to 740.
Yes. Yeah.
Nanometers. So it's ultraviolet invisible wavelengths. just going a little bit beyond the red.
Yeah, we have two CCDs, and each one cover the wavelength that Sean just mentioned.
There's a small gap in the middle.
And we do have a question online, and then I'll come back to the question in the room. Opening up your line, if you would introduce yourself first, please, and ask your question.
Hi, this is Rebecca Hersher from National Public Radio. Sorry I couldn't be there today in person. This is great. Can you just tell me a little bit more about the launch? Obviously, you're working with the folks who are building this satellite, but is the launch scheduled for April 7th still? Is it likely to be rescheduled? I know these things sometimes get pushed. And where exactly will it be launched from?
So Jean-Luc Froliger from Intelsat. So you're correct. The launch is currently scheduled for early April. April 7th is our working date. The satellite has been completed. It's going to be placed into the container today and tomorrow, and it's going to be airshipped from Moffett Field in Northern California to the Cape, right? Then it'll be processed at the payload processing facility from SpaceX, integrated into the Falcon 9 5500 launch vehicle. Launch is scheduled, as we said, April 7th, and liftoff is at 0029 Eastern Standard Time. So please stay up to watch the launch.
And as SpaceX is providing the launch, they're probably the definitive answer for launch questions. They're the place to go, but shooting for early April, and we'll certainly update should that be adjusted or get more specific. And then we had a question in the room.
Lucie Obo for AFP News Agency. I had a question maybe for Caroline about the geostationary orbit. Can you talk a little bit about what that changes to be in this orbit? And maybe for Karen, could you talk a little bit more about the new generation of satellites monitoring Earth, maybe more like a big picture question about what are the big changes, what it brings compared to the 25 missions that you already have launched? Thank you.
What was the question? Sorry, what was the question about geostationary orbit?
What does it change? Because you said usually these air monitoring satellites are not in this orbit.
Yeah. So a geostationary orbit, the planet is rotating 24 hours a day, and the satellite is at an exact altitude. It's around 35,000 kilometers or just over that. If you put it into that orbit, as opposed to the other ones that are like 700 kilometers, so it's way farther out. But if you put it into that orbit, its period of rotation is the same as the Earth's rotation. So the Earth rotates, and the satellite essentially is sitting over the equator, and it goes with the planet's rotation. So it's always over the same place, as opposed to going around like this 15 times a day. So.
All right, and one thing I'll add to that is TEMPO is NASA Earth Science first geostationary instrument. So we're really excited about that. Most of our satellites and instruments are in low Earth orbit. So again, getting lots of different attributes of the Earth system, but relatively sparse sampling in time. And that's the real power of geostationary orbit, is you get a lot, you don't get the whole globe, but where you can see, you can get a lot of rapid temporal refresh. So that's really exciting. With regard to where we're going, our next generation of satellites, and this has been true throughout the history, we're always, with the next generation, looking to answer questions that today we can't answer. So I'll give you an example. The greatest source of natural uncertainty in predicting future climate change is the interaction between aerosols in the atmosphere and the clouds and precipitation that result. I say the greatest source of natural uncertainty because, of course, the greatest source of uncertainty is how humans are going to behave, but the natural uncertainty is driven by this interaction between aerosols and clouds and precipitation. And so our one of the major missions in that future fleet that I showed you is to go after exactly that question. And that means you have to measure the properties of the aerosols at the same time that you're measuring the properties of the clouds, and we're going after understanding that process. Other future missions will also measure the health of vegetation and the amount of vegetation, because of course climate is driven by the carbon cycle, whereas weather is really about water in the atmosphere. As you look to longer time frames, you're really looking at much more global interaction that changes the system itself. So some of those are the questions we are going after in the future missions, but again, all standing on the shoulders of what we're flying today, and will be informed. The design of those future systems will be informed but by what we learn today in missions like TEMPO. Thanks.
Just one compliment on the geostationary orbit. So I was mentioned the geostationary orbit is the orbit at which the satellite rotates in 24 hours, which is the Earth's rotation, so it remains at the same place for somebody on the Earth. The SpaceX rocket doesn't put the satellite in the geostationary orbit. It puts it into an elliptical orbit, and then the satellite itself, through a series of maneuvers, using its own propulsion, it's going to get it all the way to geostationary orbit. And that takes about 2 weeks, several maneuvers, all performed by the mission team of Intelsat from Tyson here in Virginia.
We have another question in the room.
Yeah, hi, Jenny Martyr. I'm from NASA. You mentioned that TEMPO will be able to see at the neighborhood scale. Can you talk a little bit about the resolution that it will be able to see and measure pollutants at, and how that compares to low Earth orbit?
So I guess I can answer that. So the highest spatial resolution is at what we call the center of the field of regard. So if you take the whole kind of area of TEMPO that it's looking at, is I think it is 2 by 4.75 kilometers. And so, but the geometry is such that if you start like looking higher up, like farther into the north, like near the Canadian oil sands or something, it's larger because you have these higher angles that you look through. So that's the like kind of nominal resolution. And I guess neighborhood scale is kind of a funny thing to say because people's neighborhoods are very different, right? Some people who live in the country have a huge neighborhood, and some people have a very small neighborhood in the middle of a dense urban core. So maybe I should say suburban. I think I said that too. But like Laura and Erica were showing, the kind of resolution we're getting at now is sort of getting down to like being able to see variation within the city, and so people can start to use this information to get out like from different areas of the city, for instance, like who has higher NO2 and lower NO2. But the other thing we can actually do with this data, because we have so much of it, this is kind of technical, but you can do something called oversampling. So if you have a month of data and the satellite is actually moving its little footprints all the time, they're not always at the exact same spot, you can start to use these kind of more complicated averaging techniques to actually get finer resolution. So when you start averaging a lot of data together, you can start to pull out things that you couldn't see in the first, in like one scan, for instance, getting down to maybe more like 1 to 2 kilometers. Yeah.
All right, we do have another question on the phone, and then I'll go back to this one in the room. But we have a question from CNN. Go ahead and please introduce yourself and ask your question. Thank you.
Hi, thank you. This is Rachel Ramirez with CNN. You mentioned that you're working with NOAA and EPA on this. Can you just talk more about how you see this sort of fitting into Biden's overall climate agenda, especially in terms of, maybe updating climate and environmental regulations on the fossil fuel industry, especially with nitrogen dioxide, as you know, being this potent kind of planet warming pollution? Thank you.
So Tempo is going to be really good, the NO2 products be really good at finding emission sources. We won't be able to see the CO2 coming from the smokestack, but we'll be able to see the NO2. NASA does have the OCO2, the Orbiting Carbon Observatory, and the OCO3 instrument on the space station that are measuring CO2 daily with a narrow swath around the globe. We also have a new satellite called EMIT that's on the space station that can measure methane, and so we will be able to see methane emission. From that, we can see methane emission from oil wells and from landfills. It's a new product that satellite's only been up a few months, and so, but the one of the nice things about Tempo is we'll be able to work with our partners at EPA and tell them maybe you should put a monitor here. We're seeing a lot of NO2, and maybe we're not sure what the source is. And so, again, the EPA currently only knows air pollution where they have monitors. And so it's this combination of having the satellite view and the ground-based measurements together that really give us the most information. But NOAA is the official agency in the U.S. that's responsible for air quality forecasts as part of the Weather Service. And so NASA, NOAA, and EPA have been working together for decades, but this satellite is really going to add to that partnership.
This is Karen St. Germain. Again, I'll just add a couple of more thoughts. So the objective of NASA science missions is always driven by the science, the scientific understanding, making the data freely and openly available and relevant to agencies with operational missions. But principally NASA's role here is to do the science, provide the data, and enable those agencies. So we are, and that's why we can't really comment on policy implications here. We're not a policy driving agency or an enforcement driving agency. Thanks.
And we do need to wrap up. Do we have time for one last question in the room? We'll take that one last question in the room, and for anybody else who didn't have a chance to ask, we'll get you. But we're going to do it super quick. So ask your question super quick, and we'll answer super quick.
All right. This is Brendan Cullerton with Gray Television. Kind of along that line, but I was wondering if anyone could give an example of once you have better data on where pollution is coming from, how bad it is, how can that information be used to solve the issue of air pollution or better tackle it?
Let me give you one quick example. Barry mentioned the EMIT mission. This is a mission on the space station. It's also a venture class mission, and although it was built as a dust plume, and mineral composition mission, it turns out that we can see methane in the atmosphere. That is of great interest to those in the fuel extraction industries because, of course, if they have a leak in their system somewhere that's releasing methane, they want to know about it. That's a problem for them. That's lost revenue, right? So that's one example of just making an observation openly available, and decision makers, whether they are government or private sector, can take that information and go solve a problem.
Thank you all so much. We do need to wrap up. I just cut off someone who really wanted to answer your question, so I'm going to invite you two to talk afterwards just for a moment. For anybody who was not able to answer a question online, please go ahead and try to send us an email. We'll try to get that answered. It has been wonderful to be here today. I speak for Chris Browne, who extended an invitation to everyone to please look around the museum. If you are here today, we are so thankful for everyone to come here in person. And thank you so much for joining us for this media briefing.
Let us continue to dream the impossible dream that now becomes real.
Space is for everyone. We humans really are connected to the universe.
The Earth's climate is changing. We have documented the changes.